Hello everyone. We learned about the ultrasonic detector in the last class. Today, we start to learn about the probe. Through the learning of this course, I hope to achieve the following teaching objectives. 1. Master the types of probes. 2. Master the piezoelectric effect, piezoelectric materials, and their main performance parameters. 3. Know the meaning of commonly used piezoelectric ultrasonic probe models and understand the cable structure. The probe is a device that can realize the mutual conversion of electroacoustic energy, that is, transducer. According to different working principles, the probe is correspondingly divided into magneto-restrictive ultrasonic probe, the electromagnetic ultrasonic probe, laser ultrasonic probe, piezoelectric ultrasonic probe, etc. Among them, the piezoelectric ultrasonic probe is the most widely used one in ultrasonic testing. The magneto-restrictive ultrasonic probe mainly uses magneto-restrictive effect. That is, under the action of the magnitude field, the geometric size of the material will change, and conversely, when the geometric size changes, the original magnetic field can be changed, as shown in figure. Electromagnetic ultrasonic probes use electromagnetic induction technology to excite ultrasonic signals to achieve non-contact detection, but the sensitivity is low. When the laser pulse of the laser ultrasonic probe radiates to the object to be picked up, due to the interference of light waves, a high frequency, ultrasonic waves are excited on the surface of the object to be picked up. Laser ultrasonic detection has unique advantages in non-contact, non-distance, automatic and continuous detection, especially in various dangerous and harsh environments of high temperature, toxicity, and radioactivity. Piezoelectric ultrasonic probes are ultrasonic transducers made using the piezoelectric effect of certain materials. This kind of probe has simple structure, smooth electric, acoustic, and acoustic-electrical conversion, small energy loss, and can realize broadband emission of ultrasonic waves by adopting certain technical means. The piezoelectric effect is explained below. The piezoelectric effect can be divided into positive piezoelectric effect and inverse piezoelectric effect, as shown in the figure. The positive piezoelectric effect refers to the fact that when the crystal is subject to the action of an external force in a fixed direction, the internal polarization phenomenon is generated, and the charge with the opposite symbol is generated on two surfaces at the same time. When the external force is removed, the crystal returns to an uncharged state. When the direction of the external force changes, the polarity of the charge also changes. The amount of charge generated by the force on the crystal is proportional to the magnitude of the external force. The inverse piezoelectric effect refers to the phenomenon that's the amplification of the alternating electric field to the crystal causes of the mechanical deformation of the crystal, also known as the electrorestrictive effect. It can be seen that the use of piezoelectric effect can realize the mutual conversion of mechanical energy and electrical energy. Commonly used piezoelectric materials are divided into piezoelectric single crystal and piezoelectric polycrystal. Piezoelectric single crystal are anisotropic. Piezoelectric polycrystal are isotropic and must be polarized first when making wafers. The main performance of parameters of piezoelectric materials are as follows. 1. Piezoelectric strain constant D33. Piezoelectric strain constant represents the size of the strain generated when a unit voltage is applied to the piezoelectric crystal, that is D33 equals delta T U. The piezoelectric strain constant D33 is an important parameter to measure the emission sensitivity of piezoelectric crystal materials. A large value of D33 has good emission performance and high emission sensitivity. Piezoelectric voltage constant G33. It represents the magnitude of the voltage gradient produced by unit stress acting on the piezoelectric crystal. That is, G33 equals up. The piezoelectric voltage constant G33 is an important parameter to measure the receiving sensitivity of the piezoelectric crystal material. A large value of G33 has good reception performance and high reception sensitivity. 3. Dielectric constant epsilon. Epsilon equals CTA. It can be seen from this formula that when the distance and area of the capacitor plates are constant, the larger the dielectric constant epsilon, the larger the capacitance C, that is, the more electricity the capacitor can store. For piezoelectric crystals used in the ultrasonic flow detection, when the frequency requirement is high, epsilon should be smaller. Because epsilon is smaller and C is small, the charging and discharging time of the capacitor is short and the frequency is high. The electromechanical coupling conflicting K, which represents the conversion efficiency between the mechanical energy and the electrical energy of piezoelectric materials. For the positive piezoelectric effect, K equals converted electrical energy, input mechanical energy. For the inverse piezoelectric effect, K equals converted mechanical energy, input electrical energy. It should be noted that when a probe wafer vibrates, the expansion and contraction in the thickness and radial directions are generated at the same time. So the electromechanical grouping coefficient is divided into the thickness direction KT and the radical KP. KT is larger, the detection sensitivity is high. When KP is large, the low-frequency resonance wave increases and the transmitted pulse widens, which leads to the reduction of the resolution and the increase of band area. 5. Mechanical quality factor QM. The ratio of the mechanical energy E stored by the piezoelectric chip as resonance to the energy E lost in one circle. The energy lost by piezoelectric wafer vibration is mainly caused by internal friction. Then QM value has a great influence on the resolution of the probe. The larger the QM value, the smaller the loss. The longer the wafer continues to vibrate, the larger the pulse width and the lower the resolution. Conversely, the smaller the QM value, the smaller the loss, the smaller the pulse width, and the higher the resolution. 7. The frequency constant NT. According to the standing wave theory, when the piezoelectric chip resonates under the excitation of high-frequency electrical pulses, the thickness of the chip is half wavelength. It can be obtained simply by deduction. The thickness of the piezoelectric chip is related to the inherent. The product of frequencies is constant, which is called the frequency constant NT. Obviously, when the chip thickness is fixed, the natural frequency of the chip material with large frequency constant is higher. The wafer material is certain. The higher the frequency, the smaller the thickness. 8. Curie temperature TC. Piezoelectric materials, like magnetic materials, have a temperature-dependent piezoelectric effect. It can only be produced in a certain temperature range. Beyond a certain temperature, the piezoelectric effect will disappear. The temperature at which the piezoelectric effect of the piezoelectric material disappears is called the Curie temperature of the piezoelectric material and is represented by Tc. According to the explanation just now, the requirements of the ultrasonic probe for the wafer: 1. The electromechanical coupling coefficient K is larger in order to obtain higher conversion efficiency. 2. The mechanical quality factor Qm is smaller in order to obtain higher resolution and smaller blend area. 3. The piezoelectric strain constant D33 and the piezoelectric voltage constant G33 are larger in order to obtain higher transmit and receive sensitivity. 4. The frequency constant Nt is larger, and the dielectric constant Cplanar is smaller in order to obtain the high frequency. 5. The Curie temperature Tc is higher and the acoustic impedance Z is appropriate. Several type probes are described below. 1. Straight probe. Straight probes are used to transmit and receive longitudinal waves, so they are also called longitudinal wave probes. Straight probes are mainly used to detect defects parallel to the inspection surface, such as plate and forging flaw detection. As shown in the figure, its structure is mainly composed of piezoelectric wafer, protective film, absorption block, cable joint, and shell. Function of main parts of straight probe. The piezoelectric chip transmits and receives ultrasonic waves and realizes the exchange of electric acoustic energy. Protective film protects the piezoelectric chip from wear to damage. Absorption block close to the piezoelectric chip dampen the vibration of the piezoelectric chip, also called a damping block, so that it can stop as soon as possible, thereby reducing the pulse width and improving the resolution. It can also absorb the clutter on the back of the chip, improve signal-to-noise ratio, support wafer. The structure of the straight probe is shown in figure. 2. Oblique probe. The structure of the oblique probe can be regarded as a sound transmitting wedge block on the basis of the straight probe, as shown in the figure. During the flaw detection, since the wafer is not in direct contact with the workpiece, the inclined probe does not need a protective film. Oblique probes can be divided into longitudinal wave oblique probes, transverse wave oblique probes, and surface wave oblique probes. The transverse wave oblique probe is mainly used for flaw detection, which is perpendicular to the detection surface or at a certain angle, such as weld flaw detection, steam turbine, impeller flaw detection, etc. There are 3 nominal ways of the transverse wave oblique probe. One is nominal with the longitudinal wave incident angle AL. The second is the shear wave refraction as Bird-Ace to nominal. The third is nominally used in the K value. Our country most top is the third type. Dual crystal probe. The dual element probe has 2 piezoelectric elements, one for transmitting ultrasonic waves and the other for receiving ultrasonic waves. According to the different incident angles, it is divided into dual crystal longitudinal wave probes and dual crystal shear wave probes. 4. Focusing probe. Focusing probe refers to the focus state of ultrasound at a distance from the wafer. The commonly used wafer immersion or focusing probe is shown in the figure. As can be seen from the figure, the focusing probe can be regarded as consisting of the straight probe and the acoustic lens. According to the Snell's law, it is not difficult to find that the combination of acoustic lens and water realizes beam focusing. Other focusing probes are shown in figure. Now, let's talk about the probe model. In our country, The probe model should include the operating frequency, wafer material, wafer size, probe type, and other characteristics. Working frequency, expressed in Arabic numbers, is MHz. Wafer material represented by chemical element abbreviations. Wafer size represented by Arabic numbers in mm. The circular wafer is represented by diameter. The square wafer is represented by length plus width. The divided probe wafer is represented by the size before division. Types of probes, represented by Chinese pinyin abbreviating. Straight probes may not be marked. Probe characteristics. The tangent value of the reflecting angle, K value, in the steel of the inclined probe is represented by Arabic numerals. The angle of the reflection in the steel is expressed in the Arabic numerals in degrees. The connection between the probe and the flow dictator requires a high-frequency coaxial cable. This cable can eliminate the influence of external electric waves on the excitation pulse and reflected wave pulse of the probe, and prevent such high-frequency pulse from radiating outward in the form of radio waves. In summary, in this class, we have learned about the types of probes, piezoelectric effects and piezoelectric materials, and the main performance parameters of piezoelectric materials, commonly used piezoelectric ultrasonic probes, models, and probe cables, etc. The content is more, and the knowledge points are also fragmented, but they all have mutual connections. Please review them in a time after class. Thank you.